So this is the phenacetin experiment. We'll try and get through this quick. When you look up in Pavia under RX, alkyl halide groups, whether it's chlorine, fluorine, bromine, or iodine, they only list 2 peaks in their table. They'll talk about a X carbon stretch or a CH2X bend or WAG. They give us no examples of anything except chlorine, and even then, they don't show us an example of a CH2 with a chlorine on it wagging. So there really isn't any evidence to label anything as far as the iodine to carbon functional group. All we have left is the alkane structure, which is the classic, that side, the right side of 3000. So 2971, 2915, 2859. This collection would be circled. You could call that the sp3 carbon with hydrogens on them stretching. That's your alkane. The other alkane related one would be these 2 right here. These 2 could be called the C sp3 carbon H bend. Arguably the 1201 we can say, is that the iodine carbon CH2 stretching? Maybe, but I can't label that for sure because I don't have any reference spectra to indicate that's the case. As far as our starting material, we have an amide functional group, so let's focus on that one first. If we go, and we also have a para substituted aromatic ring, and we have an OH. Now, what's interesting about this region, when you have the H on a nitrogen or the H on an oxygen, you sort of have 2 absorptions and you have a little bit of broadness to this vicinity, which is kind of interesting. Don't usually see that. But let's just go over real quick to the amide section here in Pavia. And as far as amide with the NH, secondary amides have 1 band, and they're saying it's around 3300. When you look for an example of the secondary one, there's 1 hydrogen on the nitrogen, but see how even that NH stretch as he labeled it, yes, it's at 3300. It's kind of broad though. Well, we're just going to have to wing it here. Ours has a nice 3325 peak. We'll have to go on and say that the sharper peak here is most likely the NH stretch. Some of this broad structure should be associated with the OH stretch in this particular compound. We can't make out the CH3 29 something. Look how small that is. So it's not very definitive. We can't label the CH stretches of the alkane type. The aromatic carbons with hydrogen stretching might be buried in here, like 3035 and that. We have at 1654, that's going to be the carbonyl of the amide stretching. The aromatic ring stretching, carbon double bond stretching, 1610, 1564, 1506. This 3 is very likely to be the aromatic ring stretching. As far as the carbon-oxygen stretch of a phenol, and I've looked in Pavia, I don't see any really good, easy-to-see front runner, so I'm not going to label it. Para-substituted. You're only supposed to see 1 peak between 800 and 850. There's 2. Equal intensity. So I don't know which one is which in this case. I can't label it. Yes, I know one of them is, but I don't know which. The overtone for that from your Pavia book shows in the overtone region here, you're only supposed to see 2 peaks. I see 3. So I can't label that either. So I think we're pretty good for that one. We go into the product for IRs. We put on an ethyl group. And it turns out we definitely are now going to see 2981, 2927. These peaks are your sp3 carbons with hydrogen stretching. That's fine. We still have a hydrogen on the nitrogen. That peak right there matches exactly what Pavia has, a little bit higher, but that's fine. And I believe it would say we have another one at 3200. So whose ever this is, the 3287, not 100% sure exactly what that comes from. So let's go back to Pavia. What's kind of interesting, and this is not really mentioned in the box, right? It's not mentioned in the box specifically, but when you look at this secondary, 1 hydrogen on that nitrogen, He labels the bigger, broader peak, but then he points at this second peak, which is definitely at 3150 or something like that. Points at, says it actually an overtone of the 1550 peak right there, which is the NH bend, has an overtone right there. So folks, this right here obviously is going to notify us that if we see a peak roughly 1550-ish in that region, there should be an overtone that's going to be roughly twice that number right there. So we go back, and lo and behold, we do have a nice 1557 peak, which I would have, and it turns out that's 1600 peak right there with this 1509 and the 1481. That'd be the aromatic ring stretching, but the 1557 peak, which it turns out we could go back and check this one, the 1561 peak could also be part of the starting material right there, where that's the overtone combined with some OH buried in here. But you notice how this one here is much clearer. Do you see how the overall shape and pattern matches the one in the book much clearer? So the 3287 is the overtone of the NH bend, which will be 1557. We can say that quite definitively because it matches very nicely exactly with the pattern in the book under amides. The 1660, that is obviously the carbonyl stretch for the amide functional group. As far as the carbon oxygen stretch, stretch of the ether functional group, normally that's between 11 and 1300. We have a very nice candidate, which it stands to reason the 1245 is likely to be the CO stretch of the ether functional group. We can go back to the para-substituted ring, looking for one peak only. Now again, we have two 825, 838. One's a little bigger, but again, not sure which one is exactly the one we're supposed to have. With the other functional groups, there's obviously extra absorption there. So that takes care of the IR pretty much. We move on to the NMR, and we'll start with the starting material. So obviously, I always like to start with the carbonyls when they're there, and it turns out when you look in this region, that peak right here, the one furthest to the right, is the carbonyl of the amide. This carbon and this other shorter carbon, these two, are the attachment carbons. Do you see the two carbons of the aromatic ring that do not have hydrogens on them? Those are these two shorter ones right here. I don't know for sure which one's which unless you can find this online, and the reference will tell you which. The two taller peaks will be, and by symmetry, the ortho carbons to the OH are symmetrically the same, so those two ortho to OH will give one peak. The two that are ortho to the amide will give another peak that's going to be taller. That's what these two are. I don't know exactly which is which. In my spectrum that I ran, the NMR solvent was DMSO. So that little septet belongs to the NMR solvent that I used. Probably won't see it on yours. And you guys didn't run C13, so you don't have to worry about that. But if you find a C13, so obviously the only other remaining C13 peak is going to come from that CH3 group. If we look at the proton of that same compound, so obviously then the classic para-substituted pattern, the two hydrogens ortho to the OH will give one peak, which looks next door, sees one, that'll be a doublet. The two H's ortho to the amide will talk to that one type, and give a doublet. So you see two doublets, which is the classic para-substituted pattern. Exactly which doublet belongs to which side, I'm not 100% sure. You'd have to have a reference material for that. We also have an OH hydrogen and an NH hydrogen. Sometimes they show up, sometimes they don't. Now normally the NH ones I have found in practice to typically be sharper, but that's not the rule. So I'm expecting to scan through here and see some sort of broad or strange looking integrating to one peaks. So out here, and it is very much solvent dependent. If you ran yours in chloroform, those two types of hydrogens are variable and can move around on you a bit. They can be sharper, they can be broader. So there's the two of them. Now, which one is which? I don't know. So I'd circle these both and say these two peaks are the NH hydrogen and the OH hydrogen. And all that's left would be a singlet for the CH3 group, which we should find at 2.1-ish, or in this case, right at 2, integrates to 3, 2.06, or very close to that, very close to the 2. So now we can move on to the product. So there's our product. We can start with the carbonyl, and the two attachment carbons will be shorter because they're quaternary. It turns out that this one would seem to be missing a carbon. So folks, you may very well find, so let's start this way. The two attachment carbons would be shorter. These two ortho carbons and these two will be taller in the aromatic region. So you will see two taller peaks that clearly have to be those. You see two shorter ones, which normally would be the attachment carbons. That amide one, I'm pretty darn sure has to be past 155. When you look at our starting materials amide, do you see how the two para attachment carbons were here? And then the other amide one was actually way out at 167. So you can clearly see here, whoever ran this, when that peak that's emerging there, or one that was cut off, somebody cut off that peak. So just be forewarned, folks, this particular carbon is missing almost for sure the amide carbonyl carbon. As far as the methyl group attached to the OH, it will be found pretty much similar to the starting material around 23-ish. So what we're finding here is clear as day. There's a peak at 24-ish. The one at 15, the peak at 15 is going to be the methyl group of the ethyl group on the oxygen. The CH2 group is going to be found close to the triplet at 77, which is chloroform solvent. The CH2 group, 63. So that's what it sort of looks like. But we're missing the carbonyl carbon that got chopped off. Let's go to the proton. This is a nice clean example. You can see the hydrogen on the nitrogen, sort of broad, out near 10. You see the para-substituted pattern of the aromatics, the two doublets. You see the quartet, which has to come from the CH2 of the ethyl group talking to those three. Hence the methyl group talking to 2 will give a triplet, which can only be found there. And specifically that triplet is right around the center of the peak is 1.32. It's going to be in that ballpark. And then the singlet is for the methyl group on the carbonyl of the amide. Now that's a clean one. Now this is just a past students that has some more stuff in it. So I just took the liberty of saying, what other groups or other things do we have in the mix here? That's the product. We did use MEK, methyl ethyl ketone, as a solvent at some point in the reaction. We used iodoethane. Now the interesting thing is both of these have ethyl groups, which means triplet and a quartet. Okay? So I've circled in black what the product peaks would be. But you see here in red, there's a quartet, there is a triplet in red, and there's a singlet. So those three, if this triplet or the singlet was also part of the same compound as these two, then it would stand to reason it's MEK. Otherwise, let's say that one was water or something, then this triplet and quartet could conceivably also belong to iodoethane for this group when they ran theirs. The only way I could confirm or deny that would be to run the NMR of MEK and iodoethane as well, or look it up to completely determine this. But all I'm trying to show you is if you see an extra quartet or extra triplet, it could easily be one of those two candidates. Okay? So that handles the NMR and IRs.